Hello, everybody. Welcome back. Today we're going to be looking at subunit 8.7, which relates pH and the concept of pKa. So let's get started. So as I said, we're going to be looking at the relationship between pH of the environment in whatever system you're looking at and the pKa of a particular system. And the way that we are going to look at that is by using the Henderson-Hasselbalch equation, which of course, remember, is on your equation sheet, your formula sheet. No need to memorize. And I've put it up here in front of us, and let's just remember that the Henderson-Hasselbalch equation is to be used when you have the situation that is a buffer system, meaning you have a weak acid and its conjugate base is also present, or a weak base and its conjugate acid is also present. And what we're going to be looking at is, if you know the pH of the environment of your system, so that would be plugged in right here in the Henderson-Hasselbalch equation, and you would also know the Ka and thus the pKa of the particular buffer system you're dealing with. If you know these two pieces of information, you can learn the ratio of the two parts of your buffer system. You can learn the ratio of conjugate base to weak acid, or weak base to conjugate acid. And here's the relationship. Okay, I'm just going to pull that Henderson-Hasselbalch equation up once more. If the pH of your environment is less than the pKa value of your buffer system, then the acid form has the higher concentration. And essentially, that is a statement that's saving you from having to do the math. If this value right here, the pH, is less than the pKa, when you would go through and do the math and take the anti-log, you would find that this fraction right here would have the denominator as the larger value. So the acid form would have the higher concentration. And sometimes you'll see multiple choice questions that will ask this very thing. Here is the pKa value of a particular system. Here's the pH value. Which species, the conjugate base or the weak acid, has the higher concentration? And of course, the opposite would be true if the pH is greater than the pKa. If you were to go through and do the math, you would find that this fraction right here, the conjugate base form, would have the larger value than the acid form. Now, let us recall, I mentioned it on the previous slide, that a buffer system can also be made of a weak base and its conjugate acid. And these two statements at the bottom of the slide here would not be different. You just have to change the wording a little bit. If you were dealing with, let me just write this down, a weak base over conjugate acid buffer system, because there are two types of buffer systems out there. These two statements at the bottom are still true. We just have to alter them slightly. So the first statement, if the pH is less than the pKa, then the conjugate acid form would be in the higher concentration. And if the pH is greater than the pKa, I'm just going to take that word conjugate out and replace it with the word weak, then the weak base form. So remember, there are two different types of buffer systems. These statements still hold true. It's just they have slightly different vocabulary, that's all. Okay, but you'll see, as I said, in particular, multiple choice questions that will ask about this. Sometimes you'll see it in free response, and you would, if you have the numbers, you can actually do the math and calculate what that ratio would be, and then say which part of the buffer system would have the greater concentration. A particular instance where this relationship between pH of the environment and pKa comes up is in the form of indicators. So let's first define what an indicator is. Okay. We have done multiple calculations in our previous subunits where we were dealing with a titration. And one of the most important points within a titration is the equivalence point. When you are doing a titration in the lab, most acids and bases are colorless solutions. We need some sort of visual cue that we have reached the equivalence point. And that's what we use indicators for. Now, what is an indicator? Well, indicators are themselves weak acids. So all indicators are weak acids. Now, they are a bit unique in that they have color to them. In this equilibrium reaction, guys, I am using the letters IN to stand for indicator, not the element indium. And this indicator, what I'm trying to show here is that this indicator in its acid form is red in color, but in its deprotonated, its conjugate base form, it is a different color. It is yellow. And that's what makes indicators sort of unique. They are weak acids, but they're weak acids that have color to them, and they are different colors depending on if they are in their protonated, have the hydrogen attached, or deprotonated conjugate base form. What is controlling this equilibrium system, what color is it? Is it red or is it yellow? Is the pH of the environment. So indicators are perfectly suited to tell us when we have reached the equivalence point. And we're gonna look at how do you select an indicator for a particular titration. Just a little vocabulary here. If you ever see the term endpoint in a question, that just means, endpoint means when the indicator changes color. Again, that's going to tell us when we have reached the equivalence point in a particular titration. Now, there are lots of indicators out there. Can you use any indicator you want for a particular titration? The answer is no, you can't. So how do you know which indicator is best for your particular titration? Well, indicators have something called a useful range. Okay, that's a pH range where they are best suited to tell us when we've reached that equivalence point. Now remember what I said, acid-base indicators are themselves weak acids. Since they're weak acids, that means each indicator has its own Ka value, which means it has its own pKa value. And here's how you tell the useful range for an indicator. Its useful range is whatever its pKa value is, plus or minus 1. So let me give you an example. Let's say that a particular indicator has a pKa value equal to 4.0. That means its useful range would be from 3.0 to 5.0. Now, what do I mean by that? That means if the particular titration that I'm doing, if the equivalence point fell, let's say, at a pH of 3.7, then this would be a perfect indicator to use because my pH at the equivalence point falls within this indicator's useful range. Now, what if my pH at equivalence falls at, say, 9.7? Then this would not be my best choice for the indicator, okay? You want to choose an indicator, let me pull this up on the slide, whose useful range includes or is closest to the pH at equivalence for that particular titration. Sometimes you're given some options for indicators where the pH at equivalence doesn't fall perfectly within the range, but it's pretty close. That would be fine, okay? But that's how you're going to select an indicator, and we're gonna look at an example problem about that in just a second. This is a chart just showing some indicators. There are many more than what I've got listed here. And what this chart is showing you is for each of the indicators, it's showing not only its useful range, that's what those bands are representing, but also what colors they turn. For example, the second to last one, phenolphthalein, is an indicator that is really commonly used with titrations in the lab. You can see that phenolphthalein has a useful range essentially from 8 to 10, meaning this would be a good indicator to use if our pH at equivalence falls between 8 or 10. Phenolphthalein goes from colorless to pink. So let's say we are adding progressively more and more base, okay, like the acid is the analyte and we're adding more titrant base. So the pH would be going up. Once we have reached that equivalence point, we would see the solution down in the analyte, we would start to see it turning pink when we have reached the equivalence point. If any of you are wondering why the second indicator in that list, thymol blue, why does it have two bands? Remember what we said? Acid-base indicators are themselves weak acids. Thymol blue is a particular acid that is diprotic, meaning it has two hydrogens to donate, meaning it's going to have two different useful ranges. So let's look at an example problem here. This would be a classic free response kind of a question. And this problem has us looking at a titration between hydrochloric acid and sodium hydroxide. Read the problem carefully. It's going to ask us to do multiple things with this titration. So pause the video, see how you do with it. All right, so let's take this part by part. Part A says, identify the solution that was initially added to the beaker, explain your reasoning. Essentially, they're saying, based on the graph that we're given, which species, the acid or the base, is the analyte, okay? And hopefully you answered that the analyte was the acid. Now, I chose to explain this based on the fact that the initial pH in this titration was a pH of 1 in the acidic range. You could also explain it by saying that the pH is going up as more titrant is added, thus the titrant must be the base, which would make the acid the analyte. You could explain it from that perspective as well. Part B says, on the curve, circle the point that corresponds to the equivalence point. Hopefully you all, that was an easy one for you. Okay, right around at a pH of about 7. And then part C says, at the equivalence point, how many moles of titrant, meaning moles of the base, the sodium hydroxide, have been added. If you look at the graph, we know the volume of the base that was added to get us to the equivalence point, and originally in the problem they gave us the molarity. So if we multiply those, we get 0.00400 moles of sodium hydroxide. Okay, part D says the same titration is to be performed again, this time using an indicator. The problem originally told us that we were using a pH meter. Use the information in the table at the right to select the best indicator for the titration and explain your choice. Remember, the purpose of an indicator is to indicate when the equivalence point has been reached. We know that the equivalence point was at a pH of approximately 7. Now, looking at these three indicator choices, none of them actually include the pH of 7. However, Methyl red is the best choice because its color change will occur the closest to that equivalence point, the pH of 7. Its useful range is the closest to a pH of 7. Last part, it says, sketch the titration curve that would result if the solutions in the beaker and burette, remember the burette is where the titrant is housed, if those solutions were reversed. Okay, now, a few things to think about here. Okay, the acid is now the titrant. The base is now the analyte. Does that change the pH at the equivalence point? The answer is no. We just need to adjust the initial pH. The pH at equivalence point is the same, and the shape of the curve is sort of that reverse of the one that they gave us. So that was just kind of a classic example of a free response question that you could see based on not only acid-base titration, but including the concept of an indicator. So I hope you all have learned a little something today, and I look forward to seeing you next time.